Hi, welcome to Acid-Base Equilibrium. My name is Dr. English. Today we're going to begin by giving an overview of acids and bases. Specifically, we're going to look at Arrhenius acids and bases, Bronsted-Lowry acids and bases, Amphiprotic substances, conjugate acid-base pairs, and a lot of examples of conjugate acid-base pairs. So let's start off by reviewing the Arrhenius definition of acids and bases. Under the Arrhenius definition, an acid is a substance that produces hydrogen ions or a proton in water. An example of this would be hydrochloric acid. A base is a substance that produces hydroxide ions, OH-1, in water. So an example for that could be sodium hydroxide. The limitation of this particular definition is that it's restricted to an aqueous environment. Now let's talk about the Bronsted-Lowry definition of acids and bases. Under this definition, an acid donates a proton, hydrogen ion, to another substance. Under this definition, hydrochloric acid is still considered an acid. But the difference between the Arrhenius definition and the Bronsted-Lowry definition is that the definition of bases is much larger. Under this definition, a base accepts a proton, or hydrogen ion, from another substance. This is where we'll see ammonia being classified as a base. This is important because in ammonia, there needs to be a lone pair to form a coordinate covalent bond with the incoming hydrogen ion, and we'll draw that out in a moment. So one of the important things that you need to know about Bronsted-Lowry bases is they must have a non-bonding electron pair, also known as a lone pair, that it can use to bind a hydrogen ion. So you might say, well, what do you mean by that? Let's look at a structural diagram of water. So here's water right here, lone pair, right here and here. So because these lone pairs exist here and here, a hydrogen ion could come in and bond to that, giving that hydrogen a full octet. Another example might be ammonia, like we stated before. So here's a structural diagram of ammonia with its lone pair again up here. A hydrogen ion could come into this lone pair, go right here, H+1, and now it would have a so-called full octet, as it would have its two valence electrons, and the overall charge on this would be +1. And now we'd have the ammonium ion. But the only reason why ammonia can do this is because of the presence of that lone pair. Another example could be the carbonate ion. Here with the carbonate ion, there are a lot of lone pairs available that the hydrogen ion could come in and bond to. This is a Bronsted-Lowry base because it can accept a hydrogen ion. What do we mean when we talk about an amphiprotic substance? This is a substance that is capable of acting as either an acid or a base. It will act as a base when combining with something more strongly acidic than itself. It will act as an acid and donate a hydrogen ion when combining with something more strongly basic than itself. So here's an example of an amphiprotic substance, and specifically we're going to look at the behavior of water right here. Here we have water above reacting with hydrochloric acid, which we know, hey, that's an acid with a capital A. In this case, it's going to act as a base, as the HCl will fully dissociate, the hydrogen will be given over to the water molecule, and as a result, we will form the hydronium ion and a chloride ion. On the bottom, this water molecule is going to act as an acid because it's going to be donating one of its hydrogens to the ammonia. When it does, we form the ammonium ion along with the hydroxide ion. So in this case, on top, the water is acting as a base, and on the bottom, the water is acting as an acid, and it will totally depend on what it's reacting with. Conjugate acid-base pairs. An acid and a base, such as HX and X-1, that differ only in the presence or absence of a proton. If something is defined as a conjugate base, this is formed by removing a proton from an acid. A conjugate acid is formed by adding a proton to a base. So let's look at an example. We have HF plus water yields H3O plus 1 and F minus 1. In this example, the HF is our acid. So I'm going to put a little A over the top of that. If HF is our acid, then the H2O is going to be acting as our base. Now the H3O plus 1 is the conjugate acid. And the reason why it's the conjugate acid is because the HF, when it did slightly ionize, donated its hydrogen to the water. So the H2O accepted that hydrogen and as a result became the hydronium ion. Therefore, it's acidic and we call it the conjugate acid. The F minus 1 then must be the conjugate base. Again, we recognize conjugate acid-base pairs because they differ, like HF and F minus 1, by the presence of a hydrogen, or the H2O and the H3O plus 1, they just differ by a hydrogen. So that's another way of being able to recognize them. Give the conjugate base of the following Bronsted-Lowry acids. So each of these 4 examples are an acid. We want to find the conjugate base. Let's look at the first one, HiO3. So the conjugate base should differ by a hydrogen. Therefore, the conjugate base is IO3 minus 1. Notice again that they just differ by the presence of a hydrogen. NH4 plus 1, that will be NH3, so we see the difference of 1 hydrogen. H2PO4 minus 1, if we lose a hydrogen here, our conjugate base is going to be HPO4 minus 2. And finally, HC7H5O2, the conjugate base will be C7H5O2 minus 1. Give the conjugate acid of the following Bronsted-Lowry bases. So now we're given bases. We want each of these to gain a hydrogen and become an acid. So HSO3 minus 1, we want it to gain a hydrogen, therefore it will become H2SO3. F minus 1 will gain a hydrogen and become HF. PO4 minus 3 will gain a hydrogen and become HPO4 minus 2. And CO will gain a hydrogen and will become HCO plus 1. Now let's do some practice identifying conjugate acid-base pairs. So for each one on the reactant side, we're going to identify the acid and the base, and on the product side, the conjugate acid and conjugate base. Let's look at the first one. NH4 plus 1 we're going to identify as an acid. Cn minus 1 we're going to identify as a base because it has the ability to gain a hydrogen. HCN is our conjugate acid because it has gained a hydrogen, and NH3 is our conjugate base because we can see that it differs from the NH4 plus 1 by 1 hydrogen. So if we had to go and identify conjugate acid-base pairs, the NH4 plus 1 and the NH3 would be a conjugate acid-base pair, and the HCN and the CN would be a conjugate acid-base pair. Let's try the next one. CH3, 3N. Not so sure about that one, so let's come back to that. And then we have H2O. Then we have CH3, 3NH plus 1. So that must be our conjugate acid. And as soon as you see OH minus 1, that's definitely your conjugate base. And remember, the label of conjugate acid and conjugate base is always going to come on the product side. So if OH minus 1 is my conjugate base, then the H2O must be my acid because it differs from that OH minus 1 by a hydrogen. The CH3, 3N, that has got to be our base because we know that nitrogen is going to have a lone pair on it and have the ability to accept a hydrogen. And again, we can see on the product side that the nitrogen did accept a hydrogen ion, and that's the conjugate acid. So if we identify conjugate acid-base pairs again, the H2O and the OH would be a conjugate acid-base pair because they differ by a hydrogen, and the CH3, 3N and the CH3, 3NH plus 1 would also be another conjugate acid-base pair. Last one, HCHO2. Not 100% sure about that, so we'll come back to that one. PO4 minus 3. That has no hydrogens to donate, 0 hydrogens to donate. So that has got to be my base. So if that's my base, that must mean that this must be my acid. And really, if I think about this, this starts with an H, and I bet you anything that's my acidified H right there, which is going to be donated. So if that's my acid, then the CHO2 minus 1 has got to be my conjugate base. And it looks like a hydrogen ion was accepted over in the PO4 minus 3, so it becomes HPO4 minus 2, so that must be my conjugate acid. Again, if I look at conjugate acid-base pairs where they only differ by a hydrogen, everything else is the same. This is a conjugate acid-base pair right here, and this is a conjugate acid-base pair right here. Let's look at amphiprotic substances one more time. The hydrogen oxalate ion, HC2O4 minus 1, is amphiprotic. Write a balanced chemical equation showing how it acts as an acid towards water, and another equation showing how it acts as a base towards water. Okay, so let's start out by having it act as an acid. So I'm just going to put an A right there. So we're going to write HC2O4 minus 1 plus H2O. Now here we want it to act as an acid, and if it's going to act as an acid, then it's going to donate its hydrogen up in the front, and it's going to donate that hydrogen to my water molecule. So as a result, we'll have C2O4 minus 2 plus H3O plus 1. And if I was to go through and label these as acids or bases, then my water would be my base, the C2O4 minus 2 would be my conjugate base, and the H3O plus 1 would be my conjugate acid. So this is a situation where the H right here is being donated, therefore the HC2O4 minus 1 is acting as an acid. Let's see what it looks like when the hydrogen oxalate ion acts as a base this time. So HC2O4 minus 1 plus H2O. So again, the HC2O4 minus 1 is not going to donate a hydrogen. In this case, it's going to accept a hydrogen. So when it does do that, then it will become H2C2O4. The water will act as an acid because it's donating one of its hydrogens, so it will become OH minus 1. So if we had to go through here and label everything, the HC2O4 minus 1 is my base, the H2O is my acid, the H2C2O4 has to be my conjugate acid, and the OH is my conjugate base, which makes sense because if I look at the reactants and products that only differ by a hydrogen, I have the H2O and the OH, that's conjugate acid-base pair, and the HC2O4 minus 1 and the H2C2O4 as the conjugate acid. They only differ by a hydrogen, therefore they are a conjugate acid-base pair. So what did we go over? We went over the initial definition of Arrhenius acids and bases. We talked about Bronsted-Lowry acids and bases, considered amphiprotic substances, talked a lot about conjugate acid-base pairs and how to recognize them, and then we did some more examples. Need more help? Feel free to contact me. Have a great day.